Welcome back. Let's solve some example problems involving lines in 3D space. All right, so here's our first example. We want to find a set of parametric equations and a symmetric equation of the line passing through the point 0, 0, 0, which is the origin, and is parallel to the vector v, which is the position vector of the point 8, 2, 9. Okay, so if you want to represent a line in 3D space with either a set of parametric equations or a symmetric equation, you're going to need to know two things. You need to know a point on that line, and you need to know a vector that that line is parallel to. And we call that vector a direction vector. Okay, and you'll notice that in this example, we are given both of those two things that we need. We're given a point 0, 0, 0 that the line passes through, so that's going to be a point on that line, and we're given a vector that the line is parallel to. This vector right here, vector v. Vector v is the direction vector for the line in this example. This vector describes the direction of that line. Okay, and so we have both things that we need here. We have a point and a vector, but now in order to do that, we do need to know the general form of a set of parametric equations and a symmetric equation for a line in 3D. And they look like this. This first equation that we have here is the symmetric form of a line in 3D, and this second set of equations that we have here is the parametric form of a line in 3D. And you can tell pretty easily that they are parametric equations because x, y, and z are all defined with some parameter t. Okay, but now ignoring that parameter of t for now, you'll notice that both of these forms of representing a line in 3D involve these values of a, b, and c, as well as x1, y1, and z1, right? All of those values are in both of these forms. And so what do each of those values represent? Well, a, b, and c are called direction numbers. They are the components of your direction vector. The x component is a, the y component is b, and the z component is c. So in this case, we could write this down. A is equal to 8, b is equal to 2, and c is equal to 9. Those are the direction numbers for our line that we get from the direction vector. They are the x, y, and z components. All right, and then what about x1, y1, and z1? Well, those are the coordinates of the point on the line that we've been given, this specific point right here. So in this case, x1, y1, and z1 are the x, y, and z coordinates of this point, which are all 0. So x1, y1, and z1 are all 0. Okay, and so that's why you need both a point and a vector to represent a line in 3D. Both of these equations, the symmetric equation and the parametric equations, require values that come from a point on the line as well as a vector parallel to it. Okay, so that's how everything works together, but now we're at the point where we can actually begin to set up these equations. And so let's start with the symmetric equation. Let's set this one up. We're going to have x minus x1, which is 0. So we have x minus 0 divided by a, which we know is 8. So we have x minus 0 divided by 8, and then this will be equal to y minus y1, which is also 0. So we have y minus 0, and we're dividing by b, which is 2. So we have 2, all right? And then that will be equal to z minus z1, which is also 0, right? z1 is 0, and then we will be dividing by that direction number of c, which is 9. Okay, so I'll write in 9. And now all there's left to do is simplify this. X minus 0 is x, y minus 0 is y, and z minus 0 is z. So if we simplify, we'll have x divided by 8 is equal to y divided by 2, which is equal to z divided by 9. And that right there is the symmetric equation of the line passing through this point and is parallel to this direction vector. Okay? And so that's the symmetric equation. Now let's work on finding a set of parametric equations. We're going to be using the same values we used before, but just in a different way. For the x equation, we're going to have x is equal to a times t plus x1. A is 8 and x1 is 0. So we'll have 8 times t plus 0. Then for y, that will be equal to b times t plus y1. b is equal to 2, y1 is 0. So we'll have 2 times t plus 0. And then for z, that will be equal to c times t plus z1. Now c is equal to 9, and z1 is 0, so we will have 9 times t plus 0. Okay, now if we simplify, adding anything to 0 will just be itself, so this will just become x equals 8t, comma, y equals 2t, comma, z equals 9t. And that would be a set of parametric equations that would represent this line in 3D space. In particular, the line that passes through the origin and is parallel to this vector. Okay, let's take a look at a different example. Okay, so here's our second example. We want to find a set of parametric equations and a symmetric equation of the line passing through this point of -3, -3, -4, and is parallel to the vector u, which is the position vector of the point 1/4, -3/2, 1. All right, so this example is similar to our previous example. We have the same exact directions, but now we have a different point and a different direction vector. And so the process is the same. We're still going to be representing a line in 3D with two different types of equations, but now those equations are going to look a little bit different since we have a different point and a different vector. Okay, and I don't have our general formulas written down here for us to reference. It's going to be important that you memorize how to set up these parametric and symmetric equations. And so let's get started here. Before we try to write out any equations, I think it is important that we identify our direction numbers, or the components of our direction vector. But notice in this case that we have some components involving fractions, and that's not going to look very nice when we go to set up our symmetric equation, because we're going to be dividing by those direction numbers, and dividing by a fraction doesn't always look the nicest. We can certainly do it, but what I'm going to do here is try to make my equations look nicer by using a scalar multiple of this vector that will have whole numbers as its components. And that might seem weird at first, like it doesn't seem like a legal move that we can make, but it is, and I'll quickly explain why. When you want to represent a line in 3D space, you need a point on that line and then a vector that the line is parallel to. And remember that scalar multiples of vectors are parallel to each other, right? So if we found a scalar multiple of this vector with nicer components, that vector would still be parallel to this vector, which would still be pointing in the same direction, and so therefore it would still be parallel to the line that we're trying to represent. And so the bottom line here is that there are multiple different vectors that you could use to represent this specific line, as long as the vector that you are using is a scalar multiple of the original direction vector that you're given. Okay, that's why in these problems, you're told to find a set of parametric equations and a symmetric equation of the line, not the set of parametric equations or the symmetric equation, because there's going to be multiple different correct answers depending on the vector that you use. You don't have to use this specific direction vector. You could use any vector that is parallel to this vector, or in other words, any vector that is a scalar multiple of this vector. Okay, and so I want to avoid working with fractions, so what I'm going to do is multiply this vector by a scalar multiple of 4, and that will get rid of these fractions. We'll have nice components to work with a different vector. All right, so I'm going to call that vector vector v, and I'm going to multiply 4 by vector u to get that vector. And I chose 4 because it's the least common multiple, or the LCM, of the denominators that I'm trying to get rid of. The least common multiple of 4 and 2 is 4, so that's why I picked 4 in case you were wondering. Okay, and so multiplying by 4 will give us this. We'll have 4 times 1/4, which will give us 1. Then we'll have 4 times -3/2. 4 times -3 is -12, and then -12 divided by 2 is -6. So we'll have -6, and then 4 times 1 is 4. Okay? And so this is the direction vector that I'm going to use. It's still a direction vector for this line because it's still going to be parallel to that line. We're just using a scalar multiple of the given direction vector, which will still be parallel to our line. Okay, now we just have easier components to work with, or in other words, easier direction numbers to work with. All right, so our direction number A is 1, our direction number B is -6, and our direction number C is +4. All right, those are the x, y, and z components of the direction vector that we're using here. All right, and so now with those direction numbers and the coordinates from our given point, we can set up a symmetric equation to represent the line in this example. And so here's how we'll set that up. We're going to have x minus x1, or the x coordinate from our point, which is -3. So we'll have -3, and then we're dividing by that direction number of a, which is 1. And already you can see that this will be much easier to work with, right? Having a direction number of 1 is much easier than working with a direction number of 1/4. Okay, we're not dividing by a fraction, we're just dividing by 1, which is pretty nice. And let me use the right color for that so you can see where that number came from. There we go. And now that's going to be equal to y minus y1, or the y coordinate from our point, which is -3. So I have y minus -3, and then we're dividing by the direction number of b, which is -6. And once again, that is a much easier number to work with than -3/2. All right, that is why we took the time to get this nicer direction vector. But then if we continue on with this symmetric equation, we will have z minus z1, or the z coordinate from our point, which is a -4, and then we will divide by the direction number of c, which is 4. And so we divide by 4. And so now if we simplify, x minus -3 will be the same as x plus 3, y minus -3 will be the same as y plus 3, and z minus -4 will be the same as z plus 4. And so our symmetric equation will be x plus 3 is equal to y plus 3 divided by -6, which is equal to z plus 4 divided by 4. Okay, anything divided by 1 is just itself, so I didn't bother to write x plus 3 divided by 1, I just left it as x plus 3. And with that, this is a symmetric equation that would represent this line passing through this point that is parallel to this vector. But now let's find a set of parametric equations to represent this line. Remember that the x equation will be x is equal to a times the parameter t plus x1. So we're going to have 1 times t, and then we're adding the x coordinate, which is -3. So we'll have that. And then the y equation will be b times the parameter t. So we'll have -6 times t. So I'll write -6 times t, and then we add the y coordinate from our point, which is -3. So we're adding -3. And then for z, we will have c times t, the parameter. So I'll write 4 times t, and then we're adding the z coordinate from our point, which is -4. So we'll have -4. Okay, and then if we simplify what we have here, we will have that x is equal to t minus 3, y is equal to -6t minus 3, and z is equal to 4t minus 4. Okay, and so that right there is a set of parametric equations that would represent the line passing through this point, and that is parallel to this vector. Now before we move on to the next example, one thing that I do want to make a note of here is that this little trick that we just used of finding a scalar multiple of the given direction vector in order to avoid working with fractions, that little trick right there, we can only do that if we're not interested in calculating any type of distance involving this line, okay? As long as you're not going to be calculating any type of distance, which we're not going to be doing in this video, that will be in a future video, but as long as you're not calculating any distance, you can do what we did right here. If you are going to be calculating distance related to this line, then you want to use the given direction vector, because multiplying by a scalar multiple is going to affect what that distance value would be. Whatever you're calculating, it's going to be affected by that scalar multiple. Okay, so if you're not working with any type of distance, you're just trying to represent a line in 3D space, feel free to use that little trick that we did right here. Okay, let's take a look at another example. All right, so next up we want to find a set of parametric equations and a symmetric equation of the line passing through 2, 0, 2, and is parallel to the vector A, which is equal to 6j plus 3k. Okay, so this is just like our previous two examples, except now we have a different point and a different direction vector. And so let's just get started here. First thing we want to do is identify our direction numbers, which are the components of our direction vector. And you'll notice that we don't have a term with I, so our x component will be 0. So that means that a is equal to 0. and then b will be equal to 6, and c will be equal to 3. All right, 6 is the y component, and 3 is the z component. So we have b equals 6, and c equals 3. Okay, and now using these direction numbers and the coordinates of this given point, we can find a set of symmetric and parametric equations to represent the line in this example. So let's start with our symmetric equation. We're going to have x minus x1, the x coordinate of our point, which is 2. We'll have x minus 2 divided by a, which is 0. So we're dividing by 0, which is problematic. We'll come back to that. Let's just set up the rest of this equation, and then we'll talk about how we will adjust for the fact that dividing by 0 is an issue. Next, we would have y minus y1, or the y coordinate of our point, which is 0. So we'll have y minus 0 divided by b, which is 6. So we have 6. And then that will be equal to z minus z1, or the z coordinate of our point, which is 2. So we have z minus 2, and we're dividing by c, the z component of our vector, which is 3. So we'll divide by 3, and then I'm not going to box this in. This is not going to be our final answer. In order to adjust this answer such that we aren't dividing by 0 for this part of it, we're going to first find our set of parametric equations, and that will help us determine how to rewrite this one. And you'll see what I mean when we get there. For now, let's just set up our parametric equations for a line in 3D space. We're going to have x is equal to a times t plus x1. So we're going to have 0 times t plus x1, the x coordinate of our point, which is 2. Then we'll have y is equal to b times t, so we'll have 6 times t. I'll write that down, 6 times t plus y1, the y coordinate from our point, which is 0. So we'll have plus 0, and then z will be equal to c times t, so we'll have 3t. So I'll write that down, 3t plus z1, the z coordinate of our point, which is 2. Okay, now if we simplify, 0 times t is 0, right? Anything times 0 is 0. So we're just going to be left with x equals 2. So I'll write x equals 2. Then we have y equals 6t. Anything plus 0 is just itself. So we just have y equals 6t. And then we have z equals 3t plus 2. Nothing to really change there. That's going to remain the same. But that right there will be a set of parametric equations that represents the line in this example. And now that we have this, we can use it to help us finish this symmetric equation. We can't really write the symmetric equation in this way because we are dividing by 0. That's a problem. We can't leave it like this. But what we can do is remove that part of the symmetric equation, the problematic part, and just have the part that is good, and then tack on what we found x was equal to from our parametric equations. All right, so in this case, x equals 2. And we can do that because that parametric equation doesn't have the parameter in it, right? It's just x equals 2. We don't have that parameter of t there. So it's going to be fine for us to include that along with this symmetric equation. Okay, and so that's what the symmetric equation will look like in this case. But actually, we could simplify it a little bit more because we do have y minus 0 divided by 6. And so I'm just going to rewrite this again. Y minus 0 is y, so this would become y divided by 6 is equal to z minus 2 divided by 3, and then we'll have comma x equals 2. All right, so that would be the final form, or the simplified form, of the symmetric equation for this line. Okay, and so that's it for this example. Let's take a look at a different one. Okay, so here's our next example. We want to find the coordinates of a point on the line and a vector parallel to the line. And so we're given a line here. In particular, we're given a line in parametric form, right? We have 3 parametric equations that represent a line. And essentially what we're doing in this example is the opposite or the reverse of what we've been doing so far in this video, in the first 3 examples. Instead of finding a line from a coordinate point and a vector, we want to find a coordinate point and a vector from the line. And so if you've been following along with the previous examples, then the solution to this example might be pretty obvious. If we want to find a point on this line, Remember that in order to create a set of parametric equations for a line, we have to use a point on that line. The x, y, and z coordinates of that point are part of these parametric equations. In particular, the coordinates of the point are the extra values added on to the term with the parameter. So in this case, that would be this 3, this -1, and this -2, right? Those are the three values that are not associated with the term having a parameter. For this parametric equation, there is no parameter, we just have -2. And we'll talk about what that means for our vector later on, but in terms of a coordinate point that would be on this line, we can conclude that the x-coordinate is 3, the y-coordinate is -1, and the z-coordinate would be -2. And so we can write that down right away. The point will be 3, -1, -2. That is the first part of this example. We found a point on this line by just looking at those extra constant values that are being added or subtracted from the term with the parameter. Now, on the other hand, if we want to find a vector parallel to this line, that's going to be a vector that involves the direction numbers, or in other words, the coefficients of those terms with the parameter, right? Maybe I should have wrote this down to start. The general form of our parametric equations for a line in 3D are x equals a times t plus x1, y equals b times t plus y1, and z equals c times t plus z1. We already worked with x1, y1, z1. Those are the three values that we just found to make the point. Now what we're looking for are a, b, and c, the direction numbers, which are the components of a vector parallel to the line. And so those are just the coefficients of that parameter in each parametric equation. So for a, that's going to be -1. For b, that's going to be +2. And then for c, well, there is no term with a parameter for this parametric equation for z, so we can just assume that it's 0. Okay, and so what we find here is that our vector parallel to this line will have the components of -1, 2, 0. And that's it. That's a vector that would be parallel to this line. We just identify those direction numbers and make them the components of that vector. All right, let's take a look at another example. Next up, we have a similar example. Once again, we want to find the coordinates of a point on the line and a vector parallel to the line given this line right here. And once again, we're given a line in parametric form, so this should be pretty quick this time. Now that you've seen one example of this, finding a point on this line and a vector parallel to this line should be a pretty quick process. Let's start with the point. The point will have coordinates of the extra values being added on to the terms with the parameter in each of these parametric equations. So for the x-coordinate, notice that there's nothing being added on to 4t, so the x-coordinate will be 0. For the y-coordinate, you can see that we're adding 5 to our term with the parameter, so we'll have 5. And then for the z-coordinate, you can see that we're adding 4 to our term with the parameter, so our z-coordinate will be 4. All right, so that's a point on the line. And now for a vector parallel to this line, we just need to look at the coefficients of each of those terms with the parameter of t. So we will have that vector v is equal to the position vector with the components of 4, -1, 3, right? Those are the coefficients of that parameter t. We have 4, -1, and 3. That is a, b, and c, which we have identified from these parametric equations for this line. Okay, and so that would be a vector parallel to the line that we were given. For our next example, we have the same directions. We once again want to find the coordinates of a point on the line and a vector parallel to the line, and this is the line we're working with this time. You'll notice that we don't have a line in parametric form, but rather a line in symmetric form. We have a symmetric equation for this line in 3D space, and so the process is a little bit different, but as long as you remember the general form for a symmetric equation of a line in 3D, this problem is also pretty simple. Remember that the general form is that you have x minus x1 divided by a, and then that's equal to y minus y1 divided by b, and then that's equal to z minus z1 divided by c. All right, so the denominator of each of those parts of the symmetric equation make up the direction numbers of our direction vector, or the vector parallel to the line, and then the value being subtracted from x, y, and z will be the x, y, and z coordinates of a point on the line. So let's start with the point. We have x minus 7, so the x coordinate will be 7. So for our point, we'll have 7, and then for the y coordinate, y1, that will be whatever number is being subtracted from y. But now in this case, we have y plus 6, so that means that y1 would be negative 6. In order to have y plus 6, we would have to subtract negative 6, because y minus negative 6 would be y plus 6. So that means that our y coordinate is negative 6, so we'll have negative 6, and then for the z coordinate, z1, notice that we have z plus 2, so that means that z1 must be negative 2. Okay, so negative 2 will be our z coordinate, and that right there will be a point on this line. Now for a vector parallel to this line, or a direction vector, the x, y, and z components of that vector will just be the denominator of each part of that symmetric equation. So 4 is A, 2 is B, and then 1 would be C, right? Technically, this is z plus 2 divided by 1. Anything divided by 1 is just itself, okay? So we will have that vector v is equal to the position vector of the point 4, 2, 1. And that's it. That is a solution to this example. Okay, and that's the last one of these types of examples that we're going to go through in this video. And so one thing that I do want to mention is that these are not unique solutions. There are an infinite number of correct solutions to these examples. If you're just trying to find a vector parallel to this line, then any vector that is a scalar multiple of this one that we found would also be a correct vector, because scalar multiples of vectors are parallel. And so any scalar multiple of this vector would still be parallel to this line. And obviously there's not just one point on any given line. And so there are plenty of other points on this line as well, other than the one that we have right here. Finding other points is a little bit easier when you have your line in parametric form, because you can just pick a value of t to plug in and then get a specific x, y, and z coordinate for a point that corresponds to that value of t. Okay, so I just want to make a note of that. The answers that we found for the last 3 examples are not unique solutions. They're the easiest ones to find based on how we set up parametric and symmetric equations for lines in 3D, but they're not the only answers. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. Okay, so here's our last example. We want to determine whether any of the lines are parallel or identical. And we have 4 different lines to work with here. We have lines L1, L2, L3, and L4. And what we want to do is see if any of these 4 lines are parallel to each other or if they are identical. And essentially what that means, if they are identical, it means that they represent the same line. Okay, because remember, you can represent the same line in 3D space with different sets of parametric equations. There is not just one set of parametric equations for any particular line. There's pretty much an infinite number of sets of parametric equations that you could create to represent a line in 3D space, because when you create a set of parametric equations, part of them are determined by a point on that line, and there are an infinite number of points on a line in 3D space. Okay, and so that's what's going on here. Not only do we want to determine if any of these lines have the same direction, if they're parallel, we also want to determine if any of them represent the same exact line. And we'll talk about how to do that in a little bit. First, let's just begin by determining if any of these lines are parallel to each other. And in order to do that, we need to remember how to show that 2 lines are parallel, or that lines are parallel to each other. And the way we do it is we look at the direction vectors of our lines, and if the direction vectors are parallel, then the lines are also parallel. Okay, and all that boils down to is, can we show that the direction vectors for these lines are scalar multiples of each other? Okay, and so the first thing that we want to do here is just write out what the direction vectors are for each of these four lines. And so let's start with line 1, or L1. For L1, we have x is equal to 6 minus 3t, y is equal to negative 2 plus 2t, and z is equal to 5 plus 4t. And so to find the direction vector for that line, I'm going to write it as vector v1. All we have to do is identify the direction numbers from this line. And the direction numbers are simply just the coefficients of t, the parameter, in each of these parametric equations. All right, so for the x equation, the coefficient of t is negative 3, so that will be the first direction number, or the x component of our direction vector. We'll have negative 3. Then for the y component, we'll look at the coefficient of t in the y equation for this line. And so we have negative 2 plus 2t, so the coefficient of t is 2, so that will be our y component, or our next direction number. And then our last direction number, or the z component, will be found from our z equation. And as you can see, we have z is equal to 5 plus 4t, so the coefficient of t is 4, so that means that the z component, or that last direction number, will be 4. Okay, so that's the direction vector for line 1. Now let's repeat that process for these other three lines, and I'm going to go through it a little bit quicker this time. And so we're going to be looking for vector v2, vector v3, and vector v4, the direction vectors for these three lines. And so let's start with vector v2. That's the direction vector for line 2. And for line 2, we have x is equal to 6t, y is equal to 2 minus 4t, and z is equal to 13 minus 8t. The coefficients of t in these three equations are 6, negative 4, and negative 8. So those will be the direction numbers, or the components of this direction vector. So we will have 6, negative 4, negative 8. And then for vector v3, let's look at line 3, where we have x is equal to 10 minus 6t, y is equal to 3 plus 4t, and z is equal to 7 plus 8t. The coefficients of t in these equations are negative 6, positive 4, and positive 8. So for vector v3, the direction numbers, or the components of that vector, are negative 6, positive 4, and positive 8. Okay, then finally, we have vector v4, which is based on line 4. And I'm going to rewrite this vector. That's kind of ugly looking. Let's do that again. Here's vector v4. There we go. That looks a little bit better. To find the components of this vector, we want to identify the direction numbers for line 4. And the parametric equations for line 4 are x equals negative 4 plus 6t, y equals 3 plus 4t, and z equals 5 minus 6t. So the coefficients of t are 6, 4, and negative 6. So those will be the direction numbers, or the components of vector v4. So we have positive 6, positive 4, negative 6. Okay, and so now we have our four direction vectors for these four lines. Now what we want to do is determine if any of them are scalar multiples of each other. All right, because if we can determine that, then we will be able to conclude that the lines corresponding to those vectors are parallel. Okay, because if the direction vectors are scalar multiples, then they are parallel, which then in turn means that the lines are also parallel. Okay, and so let's use the first vector as sort of the vector that we were going to be comparing to, vector v1. Notice that there's no common factor that's a whole number that we can pull out of each of these components. Negative 3, positive 2, and positive 4 can't really be simplified in any way. So I'm going to use this vector as the vector we will compare to. And so let's move on to vector v2. Can we pull out a scalar value or a factor from these components that will show that this vector is a scalar multiple of vector v1? Well, notice that for the components of these two vectors, that the x, y, and z components are of the opposite sign. Right, for vector v1, we have a negative component and then two positive components. But then for vector v2, we have a positive component followed by two negative components. And so what that means is that if we were to pull out negative 1 from each of these components, that the signs would match up with this vector. So there is a possibility that they could be scalar multiples. All right, and furthermore, notice that all of the components of vector v2 are divisible by 2. So if we divide each of these components by -2, watch what happens. I'm going to write it down here. We're going to pull out -2 from each of these components. So we'll have -2 times -3, +2, +4. Right? -2 times -3 is +6. -2 times +2 is -4. And -2 times +4 is -8. So we pull that -2 out of all those components and look at the vector that we're left over with here. It's the same exact vector as vector v1. It has components of -3, +2, and +4. The same exact vector. So we can conclude here that vector v2 is equal to -2 times vector v1. Vector v1 and vector v2 are scalar multiples. So we know for a fact that line 1 and line 2 are at least parallel. Okay, so we know that so far, but I'm not going to write that down just yet because we still need to check to see if they represent the exact same line, if they are identical. Because if they're identical, then they're obviously parallel. So we'll just say they're identical rather than saying both of those things about those two lines. But we'll get back to that in a little bit. Let's work on seeing if any of these other vectors are scalar multiples of each other. And if we look at vector v3 here, notice that we have very similar components to vector v2. We have -6, +4, and +8. Essentially the same exact components except of the opposite signs. So if we were to pull out +2 out of each of these components, watch what happens. Vector v3 would be equal to that +2 multiplied by a vector with components of -3, +2, +4. Right? 2 times -3 is -6, 2 times 2 is 4, and 2 times 4 is 8. And so now notice that we have 2 multiplied by a vector that is vector v1. It has the same exact components. All right, so just like vector v2, we have now shown that vector v3 is a scalar multiple of vector v1. We could rewrite it to be 2 times vector v1. But now what about vector v4? What about this last vector right here? Well, right away, if you just look at the signs of these components, you can immediately tell that this vector will not be a scalar multiple of vector v1. And so therefore, it's also not going to be a scalar multiple of vector v2 or vector v3 because those two vectors are scalar multiples of vector v1. All right, and so here's what I mean by that. Notice that the first two components are positive and the last component is negative. Those signs are not the same or the opposite of each of the components in vector v1. We have negative, positive, positive, but then down here we have positive, positive, negative. Each of those components would either need to be the same sign or of the opposite sign in order for us to pull out some kind of scalar value from each of those components to show that those two vectors are scalar multiples. All right, so it's impossible for us to pull out any value from 6, 4, and -6 and end up with this vector right here. Okay, and so because vector v4 is not a scalar multiple of vector v1, it's also not a scalar multiple of vector v2 or vector v3, which means that line 4 is not going to be parallel or identical to any of these other lines. Line 4 is its own line, and it is not parallel or identical to lines 1 through 3. Okay, so we can forget about line 4. We can completely ignore it for the rest of this problem. We don't really care about it because now we just need to determine if any of the lines 1, 2, or 3 are identical. Okay, we know that they're all parallel, but do they represent the same exact line? And so that's what we're going to work on next here. And in order to check if any of these lines are identical, what we have to do is to see if there's a point on line 1 that is also on lines 2 and 3. All right, and so here's how we're going to go about that. First, we want to choose a point that is on line 1, and so I'm just going to pick the easiest point there is, which is the point that would have been used to create these parametric equations. The coordinates of that point are just going to be the extra value being added or subtracted to the t term, the term with the parameter in each of these equations. So for that point, the x-coordinate would be 6, the y-coordinate would be -2, and the z-coordinate would be +5. So we know that the point of 6, -2, and 5 is on line 1, we want to see if that same point is on line 2 or line 3. If it is, then we know that those lines have to be identical, because if they're parallel, there's no way that this line would have this point, but then not be the same as this line. It's kind of hard to explain with words, but imagine if we were looking at the 3D coordinate system here, and then this is line 1, and it passes through a particular point. If we know that line 2 and line 3 are parallel to this line, so let's say that this is line 2 and this is line 3, if they are parallel and pass through the same point, then the only way that they're going to still be parallel is if they are the exact same line. This line can't be parallel to this line and share that point unless it is that line, okay? So if we know that this point is on line 1, and we find out that it's also on these two lines, then these two lines would also have to be this line. There is no other possible line that they could be. They would have to be identical. Okay, and so that's what we're going to do here. We're going to see if this point is also on lines 2 and 3. But how exactly do we do that? Well, the way that I like to do it is to look at the x-coordinate here. The x-coordinate of this point is 6, and so what we can do is set that value of 6 equal to what x is equal to for line 2. And so what that looks like is this. We'll have 6 is equal to 6t. And then what we can do is solve for t, which you can very easily see is 1, right? T is going to be equal to 1. 6 divided by 6 is 1. And then we'll plug this value of t into the rest of the parametric equations for line 2 and see if we get the other two coordinates for that point, all right? Because if this point is going to be on this line, then we should get each of these coordinates from the same value of t. Not necessarily the same value of t for line 1, just the same value of t for line 2. All right, so we found that the x-coordinate is 6 when t equals 1 for line 2, and so the y-coordinate better be negative 2 when t is equal to 1, and the z-coordinate better be 5 when t is equal to 1 for this line only, line 2. Okay, and so if we can show that, then we can conclude that these two lines are identical. All right, and so if we look at the y equation, we'll have y is equal to 2 minus 4 times 1. Let's see what that's equal to. 4 times 1 is 4, so we have 2 minus 4, which is negative 2. So y equals negative 2. That checks out. The y-coordinate is negative 2, just like it should be. If that point's going to be on this line, now we just have to check the z-coordinate. And so let's see if z is equal to 13 minus 8 times t, then we'll have 8 times 1. And 8 times 1 is 8, so we have 13 minus 8, which is 5. So z is equal to 5 when t is 1, and that's exactly the coordinate we wanted to find. So now what we've shown here is that when t equals 1, the point on this line, line 2, is this point right here, the same exact point that is on line 1. So, since we know that line 1 and line 2 are parallel, their direction vectors are scalar multiples of each other, and we know that they both share a point, then those two lines have to be the same line. There's no other way that that's possible other than that those two lines are identical. Okay, and so now we know that lines 1 and 2 are identical, so let's write that down. Line 1 and line 2 are identical. They represent the same exact line, but with two different sets of parametric equations. But then let's check on line 3. Let's see if line 3 also contains this point, because then we could say that it's also identical to these two lines. In that case, we would say that line 1, line 2, and line 3 are identical. But let's not say that yet. We don't know that for sure. Let's check. We need to see if this point is on this line. So if we want the x-coordinate to be 6, we have to replace this x with 6 and solve for t. So we'll have 6 is equal to 10 minus 6t. And now let's solve for t and see when that x-coordinate is 6. And then using that value of t, we can see if the y and z coordinates are also negative 2 and 5. All right, and so if we subtract 10 from both sides of the equation, we'll have 6 minus 10, which is negative 4, and that will be equal to negative 6t. Dividing both sides by negative 6 will give us that t is equal to 2/3. And so when t equals 2/3, the x-coordinate for the point on line 3 is 6. But now let's see if the y and z coordinates are negative 2 and 5, respectively. Let's plug in 2/3 for t in this equation for y. we'll have that y is equal to 3 plus 4 times 2/3. And maybe you can already see that this is not going to be -2. 4 times 2/3 would be 8/3. And so we have 3 plus 8/3, which would be 9/3 plus 8/3. So this is equal to 9/3 plus 8/3, which is equal to 17/3. And that is definitely not equal to -2, right? That's the y-coordinate we wanted to have in order to know that this point is on this line, and we couldn't show that. Instead, we found that when the x-coordinate is 6 for a point on this line, that the y-coordinate is 17/3, not -2. All right, and so we don't even need to check the z-coordinate. That doesn't even matter at this point. Since the y-coordinates don't match up, we can conclude that this point is not on line 3, and so line 3 and line 1 are not the same line. They're not identical, they don't represent the same line, they are just parallel lines. Okay, and so we can finish up this problem by saying this. We know that line 1 is parallel to line 3. They are not identical, just parallel. And by extension, this does mean that line 2 is also parallel to line 3, but since they are identical, they represent the same line, it's kind of redundant to also write down that line 2 is parallel to line 3, because that's assumed since both of these lines are identical. And so really all we need to write down is this. Okay, lines 1 and 2 are the same, they represent the same line, and lines 1 and 3 are parallel. We don't have anything to say about line 4 because line 4 was not parallel to any of the other lines, and so line 4 is not included in this conclusion in any way. And so this right here is the final answer to this example problem. Okay, and so with that, this was the last example for this video, but if you do want to see some more examples involving lines in 3D, I do have some more available on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.